Good morning, class. Today we'll continue with some more points on crystals and the structures of solids and how atoms stack. Hi, Raksha. So I'll start with the structure of solids, which is on page 465. There's two types of solids, crystalline and amorphous. Sometimes amorphous solids are called glass. A glass is a substance that has varying bond lengths and bond geometries within the material. So typically glasses, they don't necessarily look different from the crystalline solid. For example, if you look at a piece of quartz and a piece of regular glass, they both look clear. You can see through them. They're transparent, but the quartz is much harder. It's the same chemical formula. Hi, Rebecca. It's the same chemical formula, SiO2, but in crystalline quartz, in crystalline SiO2, you have a tetrahedral structure. Each of the atoms is connected to 4 other atoms around it. It's a much harder substance, about a 7 on the Mohs scale. So quartz, a knife blade is about a 5. A good quality knife blade is about a 5 on the Mohs scale. Hi, Philip. And quartz is about a 7. So you can't scratch quartz with a knife blade, whereas window glass is about the same hardness as steel that you would use in a knife blade. Hi, Marvin. So that's the difference between an amorphous solid and a crystalline solid. The other cool thing about amorphous solids is because they have a variety of bonds holding them together, they have a wide melting point. In actual fact, they don't really have a melting point. They just kind of soften as you raise the temperature. They behave more like toffee. So when you heat glass, the hotter it gets, the softer it gets. Eventually, it flows like molasses, but it never quite becomes a liquid. And that's because of this particular property that none of the bonds are actually uniform. There's different bond lengths, different bond energies. So we have crystalline as a possible form. It has a well-defined arrangement. And you can have amorphous solid, where there is no orderly structure. For example, silicon oxide can be crystalline or it can be amorphous. So in silicon that is ordered properly will have a tetrahedral structure. And so on. You'll have the other bonds going to whatever it's connected to. And with an amorphous substance, you still have the same formula with the oxygen atoms, but it won't necessarily be tetrahedral. So on page 466, they asked you to give it some thought. So let's look at that. It asks, what is the general difference in the melting behaviors of crystalline and amorphous solids? And the answer to that question is that amorphous solids melt over a range of temperatures because of the variance of strength of the bonds throughout the material, whereas a crystal melts at a specific temperature. The best way to look at a solid is to understand its unit cell. And the unit cell is the sort of repeating brick that makes up the wall. It's the repeating unit. Of a solid. The crystalline brick, as it were. So, and when you repeat the same structure over and over and build up a lattice, you get a crystal lattice, which is a 3D array of points. Now you can have ionic lattices, you can have a lattice that you look like the kind you have with carbon when it forms diamond. There are many different types. We'll see later on that there's four main types of bonds in solids. The lattices of all crystalline compounds can be described by 7 basic unit cells. Okay, I'll show you the 3 types of unit cells found in cubic lattices. So there's primitive cubic, body-centered cubic, and face-centered cubic. When you draw a cube, you can do it by drawing 2 squares, slightly offset. I'll show you how that's done. I'm going to erase all this to give myself a maximum amount of room to show you the 3 lattices. And by the way, this is on page 466 of your text. So this is primitive cubic. So just draw 2 squares and connect all the vertices. In a primitive cubic lattice, there's an atom at each corner of the cube. Then you have what's called body-centered cubic. Same as primitive cubic with the addition of an atom in the center. Body-centered cubic. And the last type is face-centered cubic. This is probably going to be the messiest one to draw. It has an atom on each corner and an atom on each face, but only half of it is in each face. Okay, so to see the center of the cube, you can draw 3 lines that intersect. The center of the cube doesn't have an atom in it. They're all each at the face. Okay, so that's face-centered cubic. And depending on its position in the lattice, an atom might only occupy a fraction of its volume within the unit cell. So, for example, if an atom is at the corner of the lattice, there's only 1/8 of the atom in there. And to picture that, what you could do is draw another atom here, another atom in front, another atom here, another atom above. So take 4 cubes, put them together, take another 4 cubes, put them together, and you'll fully absorb the volume of that one atom in the center, which means that each cube is holding 1/8 of the volume of one corner atom. If you have, so this primitive cubic geometry has 8 1/8. So basically you have 1 atom in the unit cell for primitive cubic. In a body-centered cubic lattice, you have an atom at the center of the lattice and then 1 at each corner. So each one of these is 1/8. There's 8 times 1/8 plus the one in the center. So 2 atoms are in body-centered cubic. And if in a face-centered cubic, each one of these is half in. And there's 6 of them. So 6 halves is 3. And then 8/8 is 1. So you got 4 atoms in a face-centered cube. So depending on its position, in a lattice, an atom might only occupy a fraction of its volume within the unit cell. So in a cubic lattice, you have one atom. In a body-centered cube, you have two atoms per cell. And in this one, what was it I said again? 6 over 1/2, 3 plus 1, 8/8 is another 1, so 4 atoms per cell. There's a little table on page 467 where they show you the fraction of an atom that occupies a unit cell for various positions in the unit cell. So obviously if the atom's at the center of the cell, that's a whole atom. If you're on the face of the cube, for example, like one of these ones, then half of it is in and half of it is out. So only 1/2 of the atom is on a face-centered. If you have an edge, which I haven't mentioned yet, if you have an atom on the edge, it's only 1/4 of it absorbed by the unit cell. And if you have it on the corner, it's only 1/8. On page 467, they say, give it some thought. It says, for a structure consisting of identical atoms, how many atoms are contained in the body-centered cubic unit cell? Well, there are 2. There's 8. 8 times 1/8 gives you a total of 1. Oh, and there's 1 in the center as well, so it's a total of 2. So for I'm not going to erase this part so you can see what I'm doing. So give it some thought on page 467. For this unit cell, you have 1 in the center plus 8 times 1/8 of an atom. So the total will be 1 plus 1, total 2 atoms in the unit cell. And on the bottom of page 467, they show you the crystal structure of sodium chloride. And they show you what a matrix looks like. Basically, it's an alternating of sodium and chloride anions. I'm gonna try to draw it. I make no guarantee of a good outcome, but I'll try to show you what the matrix of sodium chloride looks like. So you draw yourself a nice big cube. And then say you start with a sodium atom at the front vertex. So we'll call this filled in circle a sodium atom, a cation, and the chloride will be an open circle. So they have to alternate. You can't have 2 positive charges next to each other because they'll repel, nor can you have 2 negative charges next to each other because they'll repel. And that's part of the reason why ionic substances are brittle. If you just displace the structure of the crystal by even just 1 atom, the whole crystal will crack, because what you're going to do is bring into close proximity similarly charged ions, and they'll repel each other. So that ionic crystals tend to be brittle because of that reason. So you have the sodium, and then a chloride, and then another sodium. If you go to the other side of the cell, you're also going to have a sodium, a chloride, and then another sodium. If you go to the middle of the unit, you'd have to put a chloride there, a sodium here, and a chloride there. And then you repeat the same pattern. If you go to the bottom, you start with the sodium, chloride, sodium, go to the other side, sodium, chloride, sodium. In the middle you have a chloride, here you have a sodium, chloride, and same pattern in the middle, except here because you have a sodium and a sodium, you got to put a chloride in the middle. Then you have a sodium here, chloride there. That's the front face. If I go to the back face, same thing. I missed one, and there's the one in the middle here. Voila, there's your matrix. I don't know if you can see that in 3D that well, but it just continues in every direction. In a perfect crystal, you'd never have any wrong atoms in there. But in real life, you do have, you know, one or two atoms that are missing, or sometimes you have a hole, you have two chlorines in one spot, so those are crystal defects, and that happens as well. And if it happens to a large extent, then you can have a place where there's a brittleness in the crystal. On practice example page 468, it says the element iron crystallizes in a form called alpha iron, which has a body-centered cubic unit cell. How many iron atoms are in the unit cell? I should maybe point this a bit more that way. Okay. It's a body-centered cubic. Okay, so in a body-centered cubic cell, this is practice example on page 468. So alpha iron is body-centered cubic, BCC. Draw your crystal. Your unit cell, I mean. And body-centered cubic means there's an atom right at the center of the unit cell and one on each vertex. So there's 8 vertices, each with 1/8 of an atom in them, totaling 1. And then the one in the center total to 2 atoms. So the unit cell holds a total of 2 atoms for the iron atom. On practice example page 469, that's a bit more fun actually, where it says the body-centered cubic unit cell of a particular crystalline form of iron is 2.8664 angstroms, which is 10 to the minus 8, 10 to the minus 8 of a centimeter, or 10 to the minus 10 of a meter. Calculate the density of this form of iron. I forgot that it was 10 to the minus 8 of a centimeter, so my calculation looks a little bit roundabout, but last night I start off at 10 to the minus 10 of a meter for an angstrom, and you'll see how that works out when I do the conversion. So the unit cell contains 2 atoms. So you have 2 atoms. Let's find out what fraction of a mole that is, because then if we know what fraction of a mole of atoms there are, we can find out how many grams of atoms we have, and from there we can find the density. So Avogadro's number 6.022 148.140857 times 10 to the 23 atoms per mole. Molar mass of iron. Actually, I wrote down how many moles that is. It's 3.321078081 times 10 to the negative 24 of a mole times 55.845 grams per mole means you have 1.854 times 10 to the negative 22 grams of iron. Okay, that's 2 atoms. That's 2 atoms of iron weighs. We're going to use density equals mass over volume. And we keep in mind that volume is equal to the length of the unit cell cubed. And we know that the length of the unit cell is 2.8664 angstroms, which is a non-SI unit. But that's no problem, we can fix that. Times 1 meter per 10 to the 10 angstroms times 100 centimeters per 1 meter. I know this is roundabout. I should have just gone to 10 to the negative 8, but I didn't remember that last night. I just did it, and then I left it after. So we get that, what is it? So L equals 2.8664 times 10 to the negative 8 centimeters. And the V of the unit cell is going to be L cubed, which equals 2.355, 1056 times 10 to the power of negative 23 centimeters cubed. So entering the values of the mass in grams and the volume in centimeters cubed, density equals mass over volume equals 1.854, etc., times 10 to the minus 22 grams over 2.355, etc., times 10 to the negative 23 centimeters cubed. You get a density equal to 7.8750 grams per centimeters cubed. And if you look up the density of iron on the periodic table, you'll see it matches it pretty well. So that's how you calculate the size of a unit. You can do that calculation in reverse. If you know the density of the metal and you know its molar mass, you can find the edge length of its unit cell, as long as you know what kind of structure the atom has, which can also be found out by somewhat more complicated calculations. This is something that forged Linus Pauling's career. He wrote over 1,000 papers all through the 20th century, a lot of times precisely dealing with the issue of what the structure of a unit cell was. Probably had a lot of calculus in there, and anyway, the man was a genius, so I imagine it took a genius to do the calculations properly. Close packing of spheres is the next thing I want to talk to you about. Crystalline solids are those that bring particles in closest contact to maximize the attractive forces between them. In many cases, the particles that make up the solids are spherical or approximately so. Such is the case for atoms in metallic solids. It is therefore instructive to consider how equal-sized spheres can pack most efficiently, that is, with the minimum amount of empty space. And there's actually two ways that you can arrange a hexagonal packed set of spheres. So if you take, for example, 7 oranges, you put 1 orange in the middle, and you can put 6 oranges around the middle orange. That's called a hexagonal pattern. So I'll show you what it looks like. So it's called close packing of spheres. Spherical atoms can be arranged in hexagonal patterns. Like oranges in a carton, if you like. So you'd have a central one, you have one on top, one below, two. So there's a hexagonal close pack. Now, if you took a layer of these and put another layer on top, they would sort of sit into the holes because the spheres have little recesses on them. So you could take one layer, put it on top, then you take another layer, and the third layer can pack back so that it lines up with the first layer. So you'll get a sort of pattern that goes A, B, A, B. So layers, on page 469, it tells you this. Layers of close packed atoms can be stacked one on top of the other. And there's two schemes that you'll see in nature. You can get AB or ABC. So in ABC, you put one layer, put the second layer, and only until the third layer do you get it lining up with the first layer. And then the pattern repeats. So you get ABC, ABC, ABC. Or you can get AB, AB, AB. And it depends on the size of the spheres that are being packed. So you can get hexagonal close packing. Or if you have ABC, you get what's called cubic close packing. And both of these have 12 neighbors, meaning if you took one atom, it's got 6 neighbors on its own level, and then it's got 3 neighbors that are directly almost touching it above it, and 3 neighbors below. So that's a total of 12. So both of these have 12 neighbors. So it's 6 on plane, 3 above, and 3 below. And both have 74% efficiency, meaning if you were to take a piece of that cube, you would see then that 74% of the volume of the atoms uses up the space of the crystal, and then there's 26% empty space. Mama, what are you doing on my notes? Hey? Why are you standing on my notes? Look what he's doing. He's a troublemaker. He's a handsome troublemaker, though. Look at him. Yeah, you guys in trouble. You like standing on my notes? Yeah, I know. Chemistry's boring, isn't it? No, it's not that bad. BCC this is on page 470. Body-centered cubic is only 68% efficient, and primitive cubic is only 52% efficient, meaning there's more empty space because the atoms don't pack as efficiently. And then the coordination number equals 8 for this one, and it equals 6 for that one. By coordination number, I mean if you were to pick any one atom in the crystal, how many atoms are directly touching it. So in BCC it's only 8, in PC it's only 6. So obviously the higher the coordination number, the better the packing efficiency, which by the way happens to be the answer. So they give it some thought question on page 470. The last thing I want to look at is the type of bonding you have in solids. So it consists of a chart. I'm not going to copy the whole chart for you. I'm just going to talk about it briefly. It's on page 470 of the text. It says bonding in solids. There are 4 types. Of crystalline solids. They are molecular, ionic, so sorry, I missed one. Molecular, covalent network, ionic, and metallic. And an example of each. Molecular would be something like any gas. So argon gas has molecular bonds, and they're caused by London dispersion forces, dipole forces, or hydrogen bonds. Water in the gas phase, steam, water in the form of steam, is held together, if at all, by hydrogen bonds when it recondenses. So that would be a molecular type of solid. Once it forms ice, once it cools down enough for those forces to overcome the kinetic energy, you get a molecular bond. Covalent network would be something like diamond. In diamond, each carbon atom is connected to 4 other carbon atoms in a covalent network with a 109.5 bond angle, so it makes diamond the hardest substance known. An ionic compound would be something like sodium chloride. And lastly, a metallic bond, and you think of any metal, sodium, iron, gold, etc. They all have metallic bonds. And one of the hallmarks of the metallic bond is that the electrons that form them are highly mobile, which is why metals can conduct electricity and why you can bend metals and shape them, because the bonds are deformable. They come under strain, and very often when you bend metals or you deform their crystal, it actually hardens the metal because it puts strain on the bond. So that's called cold working. Why do they do it when it's cold? Because if you heat a metal too much, the mobility of the atoms is increased to the point that the atoms will follow the strain on their bonds, and it'll then reduce the strain on the bonds. So if you want to cold harden a high quality piece of metal, say a hammer, one of the things you can do is use the hammer. This is in the old days. Now the metals are tempered at the shop, so they're already at their maximum state of hardness. But in the old days, before they discovered the art of tempering metal, you would buy a hammer, and over time, as you used it, because the crystal got bashed by usage, it would dislocate the positions of the atoms slightly, and it would actually harden the metal. And over time, the hammer would get tougher. I'm going to stop there. Tomorrow we'll continue with some more notes to finish off this chapter. And for homework, just read through the chapter. Chapter 11 is going to give you insight into how molecules attract each other. Okay, so see you tomorrow.